Hello, everyone. Welcome to Fresh Concrete. I think we will make a start now. This is the last of this year's Fresh Concrete events produced in collaboration between the Concrete Centre and the Building Centre. My name's Elaine Toogood. I'm Director of Architecture and Sustainable Design at the Concrete Centre, and I'm going to be hosting you today, as with all of the other events, and I will be introducing you to our speaker in just a moment. So as a reminder, or if you don't know, this is an online series of events that's been created to share just some of those wide-ranging innovative practices, new types of concrete emerging to address climate change. So these are technologies bringing a fresh approach and a fresh thinking to the way that we make and that we use concrete, and not only the way we use it in the built environment, but how we can actually construct using it. Now, all the recordings from last year's series are available online through these two links on both the Building Centre and the Concrete Centre website. And if you haven't had a chance, I urge you to have a look at those. Some really interesting and thought-provoking innovation in the manufacturing use of concrete. And you can see the wide range of different areas that were looked at there, from carbon sequestering concrete, concrete designed to be and reconstructed, and electric charging of vehicles, some self-healing concrete, innovative concrete manufacture, use of graphene, and digitized concrete. So a really wide range. So if you haven't had a chance, have a look at those. But also all of the new recordings from this year are available. 4 of them in this year, and they include Shaping Better Places. So that was about creating habitat for biodiversity using concrete from Art Ecology. They're based in the Isle of Wight. We had low carbon 3D printed concrete structural beams from Minibas, beamed into us from Denmark. The last event was low carbon magnesium based concrete from Carbonite, which include collaboration with Munich University in Germany. So it's really fantastic to see all of this international collaboration. And then, of course, today will be today's recording will also be added to those websites, and that's Growing Concrete, presented by BioZeroc in just a moment. So that is really my cue to, as an introduction to Liv Andersson, who'll be joining us in a second. She's founder of BioZeroc. BioZeroc have developed a form of bioconcrete using naturally occurring bacteria to transform waste streams. Hi, Liv. Welcome to the event. Now, she's using, or they are using waste streams to transform them into calcium carbonate, creating a cement-free concrete. And Liv's going to be explaining much more about that, the use of biotech in the creation of potentially a carbon-negative concrete. Now, you may have listened to that Fresh Concrete event previously on self-healing concrete. It's a technology that's related to that in terms of, that was self-healing specifically. The talk we gave was about improving the longevity of marine structures. And this is related technology, but it's a patent pending process, talking about the rapid production and generation of the concrete itself. But Liv is going to explain much more about that. And in fact, I believe he's also going to be giving an introduction to self-healing concrete. So welcome, Liv. You've got your camera on already, which is great. And just before we hand over the slides, I just want to remind everybody that there should be some time for questions at the end of the session. So while Liv is speaking, please do put them into the Q&A box at the bottom of the screen, and I will endeavour to ask as many of those as we have time for, but I may not get through all of them. So if you, what we plan to do, as we often do, is to share the list with BioZeroc afterwards to respond to you directly. So it's really important that if you don't want a follow-up answer, then please do ask your question anonymously, or make a note of that when you write your question, and we'll make sure that it isn't followed up, and that's very important. So there's nothing more to me to say except to hand over to Liv. Welcome. Thank you very much for taking the time to give a presentation today. So if you would like to share your screen, I'll stop sharing mine and we'll make sure that's all working. Yep, looking good. That's perfect. So I'll stop sharing my video mute and it's over to you.
Great. Thanks, Elaine. Hi, everyone. We are BioZeroc, a Cambridge-based climate tech startup using biotechnology to create ultra-low carbon cement-free concrete. In essence, we use bacteria and waste products to grow rocks that organically cement sand and aggregates together. We do this in room temperatures with low energy inputs and entirely without OPC cement. So how did we get here? I'm Liv Andersson, founder and CEO of BioZeroc. My personal background is as an architect, engineer, and sustainability scientist working in the construction industry. And every time we try to implement innovative low carbon materials on projects, we found the same barriers that I reckon many of you have experienced as well. They were either A, too expensive, B, not reliable in terms of their production or performance, or C, the sustainability claims simply were not stacking up. So together with a group of scientists, we reasoned that there must be a better way of doing this. So we asked ourselves the question, how does nature do it? Nature has already figured out how to create strong, durable, carbon negative materials. Why can't we do the same to solve the challenge and the environmental challenge of concrete production? So we essentially set out on a mission to replicate nature's own processes to create materials that quite literally last a lifetime, but don't cost the earth. And so we started our journey looking at self-healing concrete. What is self-healing concrete? Self-healing concrete is a process used to increase the durability of OPC concrete by adding bacteria to the concrete mix. When the concrete cracks, the bacteria seals the cracks by converting nutrients into limestone. So similar to how corals grow in the ocean, these bacteria quite literally grow rocks that cements sand and aggregates together. It is a low temperature, low energy process, proven to be in the realm of carbon neutrality. And while the main purpose of self-healing concrete is to increase the durability and lifespan of the concrete, research also indicates that the addition of bacteria makes OPC concrete more alkaline resistant, gives it a higher flexural strength, and improves the freeze-thaw resistance. So with these benefits in both a low carbon footprint and improved performance, why was this process only used to heal cracks? Why were people not using bacteria to make concrete from scratch? The challenge with self-healing concrete is that due to the conditions the bacteria require, the process only really works in the outermost layers of the elements. So if the element is too big or the crack is too deep, bacteria can't really fix that. So if you wanted to create a material from scratch, you could somewhat easily make thin tiles, but the larger structures will be challenging. That is, until now. BioZeroc's patent-pending technology is focused on solving this challenge. We are essentially creating a homogeneous environment for bacteria throughout large elements, making it possible to not only heal cracks, but to actually build entire structures. And whilst this might sound a bit like magic, it is surprisingly simple. We mix sand and aggregates, just like you would with normal concrete. But instead of adding cement and water, we add bacteria and feed this with our proprietary nutrient mix. The resulting concrete is lighter in color, and depending on the aggregates we're using, we can create something visually similar to conglomerate rocks. Seeing our samples in real life, people often reference materials like limestone, granite, or marble. And we are also aligning this process as closely as possible with current concrete manufacturing techniques, making it possible to utilize the majority of the infrastructure that is already in place today. And as this is an organic process, we can actually use multiple different reagent sources for our nutrient mix. So keeping bacteria, I guess, is a bit like keeping livestock. Regardless of whether you would feed your cows with grain, grass, or soybean, they would still produce milk. And in a similar way, as long as we fulfill the criteria of what our bacteria needs to be happy, they will still produce concrete. Adding to that, all of our reagents can be found in various industrial waste streams. Given this flexibility, we can actually tailor and optimize our mixture to local conditions, creating a circular solution to solve a global problem. So to summarize, we have the opportunity to create a 100% circular process with local waste streams across the globe. But the question we've all been waiting for, what does this mean in terms of actual numbers? And how well does BioZeroc perform compared to OPC concrete? To illustrate this, I've borrowed a figure from the current ICE concrete benchmark ratings for embodied carbon, LCA stages 1 to 3. This shows the relationship between specified strength on the x-axis and embodied carbon on the y-axis for 624 measured mixes across the UK. And 95% of the concrete that was measured in that study was in the range between A to F. In other words, nowhere near where we need to be to meet our net zero targets, which is in the bottom right corner of A++. And to illustrate some more examples, I've also included indications of roughly where in this diagram you would find a fired clay brick, a concrete brick, and limestone paving. Limestone paving actually goes out of the scale on carbon, but I wanted to include it as a reference since BioZeroc is effectively growing rocks as a solution to replace cement. So where in this diagram is BioZeroc? Before I say that, I need to emphasize that we are an early stage company, and as such, we do not yet have a certified EPD for our process. So the numbers I will show you are indications based on the reagents we are currently using and the reagents we expect to implement within the next few years. With that said, for 2024, we estimate our bioconcrete to be roughly on par with a 75% GGBS replacement. These credentials mainly come from removing cement and the associated process emissions. As it is already a low energy process, the main carbon savings from there will be in improving the reagent sourcing, increasing use of local materials, and increasing our waste content. So for 2028, we do expect to be further along in this process and to increase the strength while reducing the carbon footprint. As such, our final product will range between ultra low carbon to carbon negative. The biggest win of all is that we are entirely free from cement. We also do want to make it clear that we are not dependent on GGBS or fly ash, and that we do not require infrastructure for carbon capture or CO2 injections. We also do not rely on offset to achieve these numbers. In essence, we have an organic process working at room temperatures that do not require high energy inputs. So, where are we at now, and what is the current focus for BioZeroc? We want to do more R&D collaborations with architects, developers, engineers, and artists. This is to gain more traction for our innovative material, show that it's real, and show applications in real-life environments. We're currently producing prototypes in our Cambridge lab, so the next step is to start trialing this process at a manufacturing site. We are launching a project in October where we have developed a concept to allow manufacturers to trial our process at low risk without disrupting their existing production lines. We already have a few big names signed up, but if you are a manufacturer and you want to get involved, don't hesitate to get in touch. And this takes us to the next step, small-scale pilot installations. And when I say small, I genuinely mean small. as in a few square meters of low regulatory, non-structural precast products. We are currently looking at things such as blocks, bricks, brick slips, block paving. So if you want to create an innovative pattern in your brickwork, or highlight paving in a walkway, or build a small retaining wall, then please do get in touch. If you want to use this for a larger project or structural projects, then please sign up for our newsletter, as we will get in touch with you when the timing is right for those type of trials. And finally, to kick off the Q&A session, I have included a few questions that we normally get. First, how long does it take to make our material? So for nature to create rocks, that quite literally takes 1 million years. So to make this process commercially viable, we significantly have to speed things up. We achieve our final strength in a matter of days, so significantly quicker than conventional concrete, and we aim to get our initial process time down to less than 24 hours. How much does it cost to make? We don't want to give exact figures at this stage, but at scale, BioZeroc's process can be cost competitive to conventional concrete. With the introduction of a carbon tax, we can actually undercut the costs. What are the limitations of bioconcrete? Truth to be told, we're not yet sure. We are continuously improving our strengths, and we have not yet hit the limitations in what shapes or sizes we can make. So far, all the shapes and sizes we've tried have worked. Is this material certified? Short answer, no, not yet. We are about to launch a 2-year project with a research institution to independently verify our broader material performance, which will be the first step towards certification. And in the meantime, we are prioritizing collaborations with partners that have a really strong sustainability agenda in place and are as such willing to trial our products in non-structural low-risk applications. And finally, how can I support BioZeroc? Great question, one of my favorite questions. We cannot change the construction industry on our own. We need the support of all of you on this call, be it architects, developers, research institutions, manufacturers, policymakers, you name it. So if you feel like you can contribute with testing support, R&D collaborations, real-life applications, do reach out. And something you can very easily do straight away is to follow our LinkedIn page, sign up to our newsletter, share our posts, and help spread the word about what we're doing. So with that, I thank you for the opportunity to present here today, and I now welcome any questions. Thank you very much.
Thank you very much, Liv. Excellent. And we can leave that contact up on there, or maybe stop sharing screens and we can have the call. Brilliant, that's great. So yeah, excellent. And of course you did preempt some of the questions that are coming through, as you knew that you would. But I do want to build on one of the questions related to time and scalability, and of course that is to do with the curing time. So presumably this is made, there's the time to make the concrete, and that will be within a mold that determines its shape. So then at what point are you able to then, does it finish, you can strike that mold and you move to the next one? Do you want to talk a little bit about that process and timing?
Yeah, sure. Up until this point, our research has been really focused on the strength and the consistency throughout the samples. So up until this point, speed has not been the main focus of our research. So we're yet to determine exactly how far we can get in the initial demolding times. We aim to get it down in less than 24 hours.
Oh, that's very impressive. So that's pretty key to the scalability of that and the economics, I guess, as well, in terms of the manufacturing structure or infrastructure that you'll need to make into it the number of molds. Yeah, okay, great. And then So you've talked about it being at the moment early trials in terms of brick block sort of shape and scale. And I guess one of the benefits of that is that to work that's compressive strength. What sort of strength are you able to get to? Have you got through to that?
Yeah, so at the moment we have independent test data of just under 30 megapascals. But as I said in the presentation, we are continuously improving on this, and we're not yet sure how high we can get this. So yeah, we're quite confident with the numbers we've already reached, the ones that's been independently tested, but we don't really want to set a limit just yet of how far we can take that.
No, so not setting a limit, but you've had some good early results with regards to that. And I'm just working with so many questions now starting to come through, and they're all brilliant. So of course, performance and strength is one. Another one is durability with regards to different exposure conditions. So what about reaction from terms of the carbonation of that? Is that something that you've looked at? But also sulfates. Have you done any of that type of testing yet, or is that next stage?
So I suppose something that we think is really positive is the testing that's been done on self-healing concrete. So the addition of bacteria, which shows improvement across various performance categories. We will, in this project that we're starting in October, test a broader range of performances. So far, it's just simply a limitation in how much we can do with a small team in a startup environment. So compressive strength consistency has really been the first key challenge to solve, as this is really what's the core of our patent pending process.
Okay, and I guess the at the core of your process as well, people are asking about what the type of feeds are that could be used. Is that something, and is it really available globally? Is there anything more you're able to say on that? So that's the secret sauce, isn't it?
It's a very well attended presentation, which is great. We don't really want to talk too much about what goes into it on this very public conversation, but what I can say is that we are using a urealytic bacteria. So one of the main feedstocks is urea, which of course can be found in urine.
Yeah, which is pretty global.
Which is pretty global, yes.
Yeah, excellent. Okay. There's quite a few questions that have come through about, I guess that might be next stage, but or is it next stage? Is the use? A lot of concrete is obviously not unreinforced. It's reinforced concrete, provides some different opportunities for how you can use the material, of course. You've started to look at that yet, or is that next stage? Have you looked at other types of reinforcement or looked at it with steel?
Yeah, so we often get these questions of, can you reinforce it? Can you do ready mix? Can you only do precast? How big precast? And I suppose there is so much in the concrete space. I think it's no news that it's the second most used material on earth. And we have been battling the challenge of, should we try and do a bit of everything and test it for every condition? Or should we really take the resources we have and focus it to make something that is really good for a small set of applications? So right now we are focusing on becoming the highest quality, lowest cost, lowest carbon alternative to precast products. That doesn't mean we can't go broader with this technology. It just means we're trying to be focused on getting this to market as quickly as possible with what we think is the easiest route.
And that makes sense that that's within a sort of I can't say precast, pre-grown situation with regards to specific elements, and they've got a particular use. Yeah, it's one of the challenges with concrete. It's all things to all people everywhere, and actually, not all the innovation is always going to be able to do that. So I get somebody's asked a question about relative to ready mix, and but that it's not meeting that process of manufacture, is it? Or have you thought about how that would work, sort of as next stage?
We have absolutely thought about that, and as I said, we're not closing down any of those doors. at this point. It's not our key focus at this moment, and partially as well because of the regulations of how ready-mix concrete is structured. We do think that precast is the best entry point at this point in time, but no, we don't want to close down the door for that.
Yeah, so it's there's still a very wide potential out there. What about fire performance? I'm trying to look at the range of different questions that we've got there. Have you looked at its performance in terms of, well, there's two things. One is how does it perform from a combustibility point of view, but also then its ability to provide some fire resistance or insulation from fire. Have you got that far yet?
No, as I said, like just with the limited resources we have been quite limited in how broad testing can do. I mean, what gives us confidence is, first of all, the testing that has been done with self-healing concrete. And the other one is that essentially we are growing rocks. So testing on various other types of conglomerate rocks can give a good indication of how we would perform. So fire is not something we're necessarily overly concerned with at this point. Of course, it's something we will be testing.
Yeah,
it's just not on the top list of the risks that we are worried about.
No, of course. I mean, instinctively, as a mineral-based material, you know, you wouldn't expect it to be a high risk, but of course, it is one of the key benefits of constructing in mineral-based materials, concrete, and those sort of agglomerate stones, that you can achieve that easily. So yes, you can see why people would want to make sure that that was maintained if they were looking at a sort of swapping out material. So I'm trying to look, there's some very specific ones about different uses, about where it could be used, but that's early doors with regards to that. Now, I mean, is there a limitation on the sort of the size of the scale of the element? Because of course, concrete, you know, it's often used in very large homogeneous structures. That's again one of its key benefits. Of course, we know that we can create those using, you know, small scale bricks as well, because that has been done for many years on, you know, from a Roman point of view. So do you know, has it got a feel about that? I mean, presumably one of the questions, one of the very first questions that was asked actually was to do with the life of the microbes or the bacteria, and I guess that's related to that question as well, or is it not?
Not really.
Okay.
I mean, I said, like, we don't know what the limitations are yet. Since we are still doing this in our lab, we're simply limited with how much we can actually produce. So for all the shapes and sizes we have tried to date, it has worked. So there might well be a limitation in thickness. We just don't know what it is yet.
So
and we're going to need to scale it up to, to test that.
So you haven't set one off and let it grow and just see how far it could. You haven't just kept feeding something to see how big it could get yet. You've been doing it within defined.
Not really, because if we would do that, it would more be a layered approach, and that's not really what we are trying to do. We are trying to make this sort of one shot where you don't have to add and add and add, but you can just do it in the sort of first attempt. So yeah, you could do that, but it wouldn't really prove anything about the process.
Okay, no, that's good. I mean, it's so completely different from anything else. You can understand that there's very different range of questions coming through to get your head around its potential. Now there are still very many questions coming in, so please, if you would like, please do keep asking them, because as I said, that we will forward them on. But one of the questions that we always get asked, and I think it's very important to be aware of, is the end of life scenario, and what's in the material and what was anticipated that would happen. One is lifespan and durability in terms of that, but then what at the end of life, is there anything that there would need to be a concern about in terms of what is made out of? It's made out of, and
there is nothing in the materials with any of the streams that we've looked at the moment that would make us concerned from end of life, anything different from other stone-based or concrete-based products. So similar to how you can crush that up and use as aggregates in other applications, you would be able to do with bioconcrete as well.
Excellent. Great. I thought that would be the answer, but thank you very much for that. So I think that is, we're now just at time. I just wanted to say thank you very much for your presentation. It was very clear and has given a real insight to the technology. And what I just wanted to do as a final finish is to share my final slide, and which is this one. To thank you for that talk and for everybody who asked the questions. And as a reminder to please do look out for our Fresh Concrete events coming up next year, and catch up on those that you've missed previously on both the Building Centre and the Concrete Centre website. And of course, if you're interested in innovation and research and development of concrete, there's other places that you can look. And we've been developing these within a range of resources within the Concrete Centre, which include the Concrete Futures online publications and webinars, exhibition at Future Build trade show, where we actually highlighted BioZeroc as well, and hope to include maybe a brick in next year's show, as well as the regular innovation features that we have in Concrete Quarterly, and various different talks and events around the calendar, which you could have a look on our website. So please do keep in touch. There is a huge amount of work going on within this field. It's the most exciting time that I've lived through with my understanding within concrete, in terms of the amount of innovation that's happening and the doors that are open to be able to take those innovations forward. So thank you very much again, Liv, and to BioZeroc for their time today. And thank you all for listening, and have a good afternoon.
Thanks, everyone.